Provisional patent disclosure and white paper preprint. Unified electromagnetic surface propulsion platform. Phase-driven magnetic traveling wave technology for industrial conveyance, smart road propulsion, vertical surface drive, and cylindrical flow systems. Notice of intellectual property rights. The concepts, systems, and methods described in this document are the original invention of Chris D. Sellye. This disclosure is filed to establish a priority date and to provide constructive notice of inventorship. Unauthorized use, reproduction, or commercialization of the described technology without the express written consent of the inventor is prohibited. Abstract. This disclosure describes a unified electromagnetic surface propulsion platform, a novel technology in which a phase-sequenced, frequency-controlled magnetic traveling wave, generated by a stationary coil array embedded in a surface, propels a magnetically coupled body along or through that surface with no mechanical drivetrain, bearings, lubricants, or moving parts beyond the driven body itself. The platform scales from hermetically sealed food-grade industrial conveyor belts through smart road vehicle propulsion with physical speed enforcement, to vertical and three-dimensional surface drive on building facades and tunnels, and finally to cylindrical wave pipe systems for drainage, snow removal, and fluid transport with integral resistive self-heating. All four application tiers share a common electromagnetic architecture. Manufacturing substrate and solid-state drive electronics, enabling a single technology platform to address a broad spectrum of industrial, municipal, and transportation infrastructure challenges. 1. Field of the invention. The present invention relates to electromagnetic propulsion systems employing traveling magnetic wave fields generated by phase-sequenced linear coil arrays. More particularly, the invention concerns a scalable platform technology applicable to hermetically sealed industrial conveyor systems, road surface vehicle propulsion and speed management, vertical and three-dimensional surface locomotion, and cylindrical wave-driven flow and thermal management pipe systems. 2. Background and prior art. Linear induction motors are well established in the art, having been applied to maglev trains, people movers, and industrial actuators. In conventional limb configurations, a stationary primary winding generates a traveling magnetic field that induces eddy currents in a passive conductive secondary, producing propulsive force through electromagnetic interaction. Existing limb conveyor systems suffer from several limitations. The reaction secondary is typically a rigid aluminum plate, precluding flexible belt operation. Air gap maintenance requires precision mechanical guiding systems. Exposed mechanical components such as bearings, rollers, tensioners, and drive pulleys preclude use in sterile or chemically aggressive environments. Speed control requires mechanical intervention or complex multi-stator switching, and the technology has not been extended to vertical surface locomotion, smart road propulsion, or cylindrical flow applications. Flexible magnetic composites employing bonded rare earth or ferrite particles in elastomeric matrices are known in the art. However, their application as a phase-aligned traveling wave secondary in a linear induction architecture, particularly as a self-propelling flexible belt, road topping, or pipe lining, has not been disclosed. Smart road systems employing embedded sensors, wireless communication, and variable signage for speed management are known. But no prior art discloses a road surface in which the physical mechanism of vehicle propulsion is itself the speed limiting factor, thereby making speed limit enforcement a physical property of the infrastructure rather than a legal constraint. The present invention addresses all of the foregoing deficiencies through a unified platform architecture described herein. 3. Summary of the invention. The present invention provides a unified electromagnetic surface propulsion platform comprising in its most general embodiment a stationary primary assembly comprising a plurality of electromagnetic coils arranged in a linear, planar, or cylindrical array along a propulsion axis, energized by a polyphase alternating current source at a controlled frequency to generate a traveling magnetic wave field. A magnetically coupled secondary comprising a flexible or rigid composite substrate incorporating a spatially periodic magnetic pole pattern aligned in phase with the primary coil array. and a solid-state variable frequency drive control system governing the frequency, phase sequence, and zonal energization of the primary coil array. The secondary is propelled along the primary assembly at a velocity determined by the traveling wave speed, which is the product of twice the pole pitch and the drive frequency. Direction reversal is achieved by transposing any two of the three drive phases, requiring no mechanical intervention. Zone-by-zone independent control is achieved by segmenting the primary array into independently driven sections. The platform is realized in four principal application configurations as described in Section 5. 4. Reference design parameters. The following parameters define the baseline industrial conveyor embodiment from which all other tiers are scaled. 5. Detailed description of preferred embodiments. Detailed description of preferred embodiments. 5.1 Tier 1 Hermetically sealed industrial and food-grade conveyor. In the Tier 1 embodiment, the primary coil array is housed within a rigid, non-ferrous structural frame and fully encapsulated in a thermally conductive epoxy compound. The frame presents a flat upper surface with a nominal 1 to 3 mm recess in which the magnetic composite belt travels. The belt is fabricated from a magnetically encoded silicone or PTFE composite with no mechanical joints, seams, or fasteners along its operative length. The exterior belt surface may incorporate food-grade texturing, static dissipative coatings, or pigmentation as required. The absence of bearings, rollers, oil reservoirs, and shaft penetrations renders the Tier 1 system inherently compatible with USDA, FDA, and EU food contact hygiene standards. The sealed coil assembly withstands high-pressure washdown with caustic clean-in-place chemistry without ingress protection concerns. The belt surface is the only process contact element, and it is fully replaceable without tools by sliding it axially off the track frame. Zone control and accumulation. The 10 meters track is divided into independently controlled zones of 1 to 2 meters each, driven by separate VFD outputs sharing a common phase bus. This enables package accumulation without back pressure contact between items. Independent speed ramping per zone for gentle product handling, bidirectional operation within any zone independently of adjacent zones, and complete de-energization of unoccupied zones for energy conservation. 5.2 Tier 2 Smart Road Surface Vehicle Propulsion. In the Tier 2 embodiment, the primary coil array is embedded within the road substrate beneath a magnetically active road topping of 20 to 40 mm thickness. The road topping comprises a wear-resistant polymer composite incorporating a spatially periodic magnetic pole pattern at a pitch appropriate for vehicle coupling. The pole pitch for road applications is scaled to 60 to 120 mm to accommodate the larger receiver plate area and higher force requirements of automotive payloads. Vehicles operating on the smart road surface carry a passive or actively phased magnetic receiver plate on their undercarriage, positioned within the coupling air gap of the road surface field. The receiver plate may be a permanent magnet composite panel or a powered phased winding array. Physical speed governance. The synchronous speed of the traveling wave field constitutes an absolute upper bound on vehicle speed within any road zone. A vehicle cannot exceed the wave velocity without losing magnetic synchronism, at which point propulsive force drops to zero and a gentle electromagnetic drag is experienced. This makes speed limit enforcement a physical property of the road infrastructure, not a legal or sensor-based constraint. Zone boundaries are defined by the drive controller segmentation. Transitioning between zones is seamless from the vehicle's perspective. Energy and thermal features. Resistive losses in the coil array are dissipated as heat through the road surface topping. This waste heat is sufficient, at normal drive duty cycles in cold climates, to maintain surface temperature above 0 degrees Celsius, preventing ice and snow accumulation without dedicated heating infrastructure. Regenerative braking is implemented by operating decelerating zones in generator mode, returning kinetic energy to the grid through the drive inverter. 5.3 Tier 3 – Vertical and three-dimensional surface locomotion. In the Tier 3 embodiment, the primary coil array is embedded in a vertical surface such as a building facade, tunnel wall, or inclined structure. The traveling wave field operates identically to the horizontal case. However, the force vector delivered to the vehicle has two components, a tangential component along the surface, and a normal component perpendicular to the surface. For stable vertical locomotion, the normal attractive force must meet or exceed the gravitational weight of the vehicle plus dynamic load factors. This requires higher flux density than the horizontal case, achievable through increased coil current density, reduced air gap, or use of active vehicle side coil arrays that amplify the coupling interaction. Active phased coupler. In the preferred Tier 3 embodiment, the vehicle carries an active phased coupler array on its contact face. This array is driven at the same frequency and pull pitch as the road surface but with a controllable phase relationship, enabling maximization of normal force for adhesion, maximization of tangential force for acceleration, vector steering of the force resultant for cornering on curved surfaces, and emergency detachment by phase opposition. The active coupler effectively transforms the vehicle into a cooperative participant in its own propulsion, rather than a passive secondary, dramatically increasing system efficiency and capability. 5.4 Tier 4 – Cylindrical wavepipe systems. In the Tier 4 embodiment, the planar coil array is formed into a cylindrical geometry, producing a traveling wave field that propagates axially through the pipe bore. Material within the bore, water, slurry, granular solids, or air, is entrained by the traveling wave and conveyed axially without pumps, impellers, valves, or any moving mechanical components. The pipe wall comprises three concentric layers from exterior to interior, a structural shell of non-ferrous composite or polymer. The embedded coil array, circumferentially wound and axially phased, and a magnetic composite inner lining presenting the pull pattern to the bore. The bore diameter for the reference design is approximately 160 mm, suitable for municipal drainage applications. Self-heating and ice prevention. Resistive losses from the coil array are conducted inward through the magnetic composite lining to the bore wall. At operating power levels, the bore wall temperature is maintained above 0 degrees Celsius regardless of ambient temperature, preventing ice formation and ensuring continuous flow capacity in winter conditions. The heating effect is a consequence of normal operation and requires no separate thermal management system. Bidirectional flow control. Flow direction is reversed instantaneously by transposing two of the three drive phases, requiring no mechanical valve actuation. Zone-by-zone flow control enables differential pressure management, surcharge buffering, and selective routing within a pipe network entirely through software commands to the drive controllers. 6. Summary of key innovations. The following aspects of the invention are believed to be novel and non-obvious over the prior art. 1. The use of a phase-aligned magnetic composite flexible belt as the traveling wave secondary in a linear induction architecture, enabling belt-type conveyor operation with no mechanical drive components. 2. Hermetically sealed coil array construction for food-grade and chemically aggressive conveyor environments, with a replaceable magnetic belt as the sole process contact element. 3. Zone-segmented independent drive control of a continuous belt surface enabling accumulation without back pressure, bidirectional zonal operation, and energy-optimized zone de-energization. 4. A road surface topcoat incorporating a spatially periodic magnetic pole pattern and an underlying coil array, wherein the road surface itself serves as the propulsion stator for vehicles traversing it. 5. Physical speed governance through traveling wave synchronous velocity, rendering speed limits an intrinsic physical property of road zone infrastructure. 6. Integral road surface self-heating through coil-resistive losses, providing passive ice and snow prevention as a byproduct of propulsion operation. 7. Vertical and three-dimensional surface locomotion through combined normal attractive and tangential propulsive force components of the traveling wave field, with active phased vehicle coupler for force vector steering. 8. Cylindrical traveling wave pipe systems for pumpless fluid and material transport, with integral self-heating bore walls and software-controlled bidirectional flow. 9. A unified manufacturing platform, magnetic composite surface over embedded phased coil array, applicable at all 4 application scales using common materials, drive electronics architecture, and control software. 7. Claims. The inventor claims as the invention the following. 1. A propulsion system comprising a primary assembly including a plurality of electromagnetic coils arranged along a propulsion axis and energized by a polyphase alternating current at a controlled frequency to produce a traveling magnetic wave field. And a secondary comprising a flexible or rigid magnetic composite body incorporating a spatially periodic magnetic pole pattern aligned in phase with said traveling wave field, wherein said secondary is propelled along said propulsion axis at a velocity equal to twice the pole pitch multiplied by the drive frequency. 2. The propulsion system of Claim 1, wherein the secondary is a continuous flexible belt fabricated from a bonded rare earth or ferrite particle composite in an elastomeric matrix, and the primary assembly is a sealed, non-ferrous planar track. 3. The propulsion system of Claim 2, wherein the primary assembly is encapsulated in an electrically insulating, chemically resistant compound and presents no exterior mechanical moving parts, bearings, or fluid seals. 4. The propulsion system of Claim 2, further comprising a plurality of independently controlled drive zones along the primary assembly, each zone operable at a distinct frequency, phase sequence, or energization state. 5. The propulsion system of Claim 1, wherein the primary assembly is embedded beneath a road surface topping comprising a magnetically active polymer composite, and the secondary is a receiver plate mounted on the underside of a ground vehicle, whereby the road surface propels the vehicle and the synchronous wave velocity constitutes the maximum vehicle speed within the road zone. 6. The propulsion system of Claim 5, wherein resistive losses from the primary assembly coils are conducted through the road surface topping to maintain surface temperature above 0 degrees Celsius during normal operation. 7. The propulsion system of Claim 5, wherein the receiver plate is an active phased coupler array driven at the drive frequency of the road primary, with a controllable phase relationship enabling vector steering of the combined normal and tangential force components. 8. The propulsion system of Claim 1, wherein the primary assembly is embedded in a substantially vertical or curved surface, and the traveling wave field simultaneously produces a normal attractive force retaining the secondary against the surface and a tangential propulsive force driving the secondary along the surface. 9. The propulsion system of Claim 1, wherein the primary assembly is formed into a cylindrical geometry and the secondary is a fluid, slurry, or granular material within the bore, whereby the traveling wave field entrains and conveys said material axially through the bore without mechanical pumping elements. 10. The propulsion system of Claim 9, wherein resistive heating from the primary assembly maintains bore wall temperature above 0 degrees Celsius, preventing freezing of conveyed material. 11. The propulsion system of Claim 9, wherein flow direction is reversible by transposing any 2 phases of the polyphase drive current without mechanical valve actuation. 12. A method of propulsion comprising generating a traveling magnetic wave field along a surface by sequentially energizing a plurality of electromagnetic coils arranged along said surface with a polyphase alternating current, and coupling a body bearing a spatially periodic magnetic pole pattern to said traveling wave field such that said body is propelled along said surface at a velocity proportional to the drive frequency. 13. The method of Claim 12, wherein drive frequency is varied continuously by a variable frequency drive controller to achieve infinitely variable speed between 0 and a design maximum without mechanical transmission. 14. The method of Claim 12, wherein direction of propulsion is reversed by transposing any 2 of the 3 phases of the polyphase alternating current. 8. Abstract of the disclosure. A unified electromagnetic surface propulsion platform is disclosed in which a traveling magnetic wave, generated by a phase-sequenced coil array embedded in a surface, propels a magnetically coupled secondary body along or through that surface. The platform encompasses 4 application tiers sharing a common electromagnetic architecture, hermetically sealed, food-grade industrial conveyor belts with zone-independent speed and direction control. Smart road surfaces that propel vehicles and enforce speed limits as physical properties of the infrastructure. Vertical and 3-dimensional surface drive for building facades and complex geometries, and cylindrical wave pipes for pumpless fluid transport and drainage with integral self-heating. All tiers share the same manufacturing substrate, solid-state drive electronics, and control software architecture. The invention establishes a new class of infrastructure-embedded propulsion technology with broad industrial, municipal transportation, and smart city applications. 9. Inventor Statement and Certification. I, Chris D. Sellye, hereby certify that I am the sole original inventor of the technology described in this disclosure. The inventive concepts described herein originated with me through independent reasoning and creative synthesis, and to the best of my knowledge and belief, the claimed inventions are novel and non-obvious over the prior art known to me. This document is filed as a provisional disclosure to establish a priority date. It is my intention to pursue formal patent protection for the inventions described herein. All rights are reserved. Date: June 4, 2026.